Let's take a look at inverse variation here. So inverse variation simply means that as x increases, the y value is going to decrease, or as y increases, x is going to decrease. And we can make the statement that y varies inversely as x, and that's what we're seeing here. Y varies inversely as x. And notice, if you remember the term inverse, it means 1 over, like reciprocal. So their x is in the denominator. It's like 1 over x. But here it's varying with some constant, so k over x. In most applications, x and y are positive, and the graph is going to look something like this at the right here. Whereas x increases, so x goes 1, 2, 3, bigger and bigger, y is decreasing. What I want you to notice is that the product of x and y at any of these given points in the curve is 1. So like here, the product is really 2 times a half, which is 1. This is 1 times 1, which is also 1. This is 2 times 1 half, which is also 1. So we're seeing that the product at any point in the curve is just some constant, in this case 1. It could be any constant. One obvious application is the formula we've already studied, and that formula is d equals rt. And what we're going to notice is that if we think of traveling a certain distance d, like let's say it's a constant, so from home to school, so some value or some distance d you're traveling. As the rate we travel increases, or as we travel faster, what happens to the time? Well, the time decreases. Okay, so if this goes up, this has to go down for this to be some constant. Okay, which is really somewhat of this equation here. Okay, this is the constant, in this case d. X and y are like r and t. As r goes up, t goes down, or as x goes up, the y value goes down. Okay, let's take a look at the first example. If c is inversely proportional to d, or varies inversely as we've said, and c is 2 when d is 3.6, find the following. Find c when d is 4.5, and find d when c is 6.4. So let's take a look at part A first. So for part A, what we're going to notice here, we've got the following. We know that c is inversely proportional to d, so that's what we start with. And we want to know, or we're told when c is 2, that d is 3.6. But if we want to find other scenarios, we need to know what the constant is. So let's solve for k first. So solving for k, we get cd. How do I do that? Multiply both sides by d, gets rid of that d. cd, okay? So k is defined as cd, which is the product of the two variables given here. So if you want to get k, you just do c times d. Okay, c is 2, d is 3.6. 2 times 3.6 is 7.2. That's the k value. Now let's go take a look at part A. For part A, we know again, we'll remember c is equal to k over d, but k is 7.2 we solve for. And for this part, they want to know what c is when d is 4.5, so let's just plug in 4.5. And what we're going to end up getting here for this, when we do 7.2 over 4.5, is 1.6. Alright, let's take a look at part B. Now part B, same starting point. But now we want to find d when c is 6.4. So we want to find d now. So in this problem, we have to get d by itself or isolate the variable d. To do so, we can multiply both sides by d and then divide both sides by c, or just notice that c and d can switch spots. Okay? So let's go ahead and do that. If we plug in the value given for c, which is 6.4, we're going to end up with a value of d close to 1 at around 1.125. Okay, example number 2. For cones of equal volume, the height is inversely proportional to the square of the radius of the base. If the radius of a cone is 10 centimeters and its height is 15 centimeters, find the radius of a second cone of equal volume with a height of 60 centimeters. So here we've got an example where not only is it inversely proportional, but it's the square of the radius of the base. So for cones of equal volume, the height is inversely proportional to the square of the radius of the base. Now again, we're going to have to find some other scenarios, so let's find our constant k. So k is going to be hr squared, if I take this r squared quantity right here and multiply it up on this side. Multiply r squared on both sides so these cancel, leaving r squared up here. Now, what we're going to notice is that if we plug in, let's go ahead and do so. We're going to have h, which was given as... So we plug in 15 for h, we plug in 10 for r, giving us 15 times 100, or 1500 for the k value here. So k turns out to be 1500. Now, remember, once you get the k value, you have to plug it back into the general form. So we again say h equals, now it's 1500 instead of the k that was up here earlier. So it's 1500 over r squared. And what we look at now is look at the next part of the problem. It says find the radius of the second cone. So find this r value of equal volume. Obviously they have to be equal volume, our statement in the beginning, with a height of 60. So h is going to be 60, and we need to find what r is. So since we're finding what r is, we should switch these spots, which gives us r squared equals 1500 over h. And we're trying to find r, so let's take the square root of both sides. So 1500 over h under a radical. Now, why don't I put a plus or minus in front of that radical? Simply because r is going to be a positive root. We know that we're looking at the positive root because we're looking for the radius, which is a length here. So r is simply 1500 over h. But again, in the second part of the problem, it says find the radius when the height is 60. So let's just go ahead and plug in. So r is going to be 1500 over 60 all under the radical, and that's going to give us a result of simply 5 centimeters. The next we want to look at is a combination of direct and inverse variation. Your book calls this joint variation, and a lot of other resources do as well, but it's really a combination of direct and inverse variation. So there's many important physical laws that combine types of variation. A good example of this is Newton's law of gravitation, and this states that the force of attraction, the force of attraction between any two spherical objects or bodies is directly proportional to the masses m1 and m2 and inversely proportional to the square of the distance r between their centers. So here what we're noticing is that we've got our constant of proportionality or constant of variation. These are directly related because they're in the numerator, right? Directly related, like f equals kx. And this is inversely related, like f equals k over x, or over r squared. So this is just one of the many examples of this. Let's take a look at a new example now where we have an actual problem set up. The problem says the electric field produced by a charged particle varies directly with the charge on the particle and inversely as the square of the distance from the charge. Okay, so let's write that out. The electric field produced by a charged particle varies directly, so kq, with the charge on a particle. Q in physics is traditionally charged, so we'll use Q for now, and inversely as the square of the distance from the charge. And the distance sometimes is represented by r. So for the sake of this problem, we'll say that Q is the charge and r is the distance. So for a problem like this, we're told that on a planet galaxies away, the electric field felt at a distance of 13 meters from a charge is 25 newtons per coulomb, when the charge on the particle producing the field is 8 coulombs. Determine the charge that would produce a field of 18 newtons per coulomb at a distance of 11 meters. So I know the units seem a little confusing at first, but these are just standard units for charges, forces, and distances. What we can really look at is take a look at our numbers here. Since we're going to need to determine another scenario, we again have to find the k value to start this problem. And this gets a little tricky to solve for k here. So let's go ahead and do that first. So to get rid of this r squared down here, we're going to multiply both sides by r squared. It'll bring it up here. And then get rid of the q that's next to the k. We're going to divide by q. So the r squared is going to get multiplied or brought up here, and the q is going to get divided or brought down here. So solving for k, we're going to get k equals er squared over q. electric field times distance squared over the charge. And we're told what the electric field is. Electric field is 25 newtons per coulomb. We're told the distance is 13 meters. We are told that the charge is 8 coulombs. That'll give us a K value of approximately 528. Now, given that value, or after determining that value, we can write okay, 528Q over R squared. And now the problem asks, determine the charge that would produce a field of 18 newtons per coulomb at a distance of 11 meters. So find the charge, so determine the charge, so find Q, that would produce a field, E, of 18 at a distance of 11. That's the R. So for this problem, what we want to do is say to ourselves, alright, we're looking for Q. Determine the charge. It says determine the charge. So we have to solve for Q. So to solve for Q here, it's like the way we solved for K a minute ago. Multiply both sides by R squared to get rid of this R squared, bring it up here, and then divide by 528 this time. So Q is going to become ER squared over 528. Now, we're given in this last part that the value of the electric field is 18 newtons per coulomb at a distance of 11 meters. So 18 newtons per coulomb at 11 meters, all over 528. And that value is 4.125 coulombs. How do I know it's coulombs? Simply because the original charge we started with was also given in coulombs. For the last problem, let's take a look at an example of engineering application again. The period of oscillations of a mass moving in simple harmonic motion is proportional to the square root of the mass m and inversely related to the square root of the spring stiffness K. The period of oscillations is 9.2 seconds when the mass is 150 kilograms and the spring stiffness is 70 newtons per meter. What mass would produce oscillations of 15 seconds when attached to a spring with a stiffness of 40 newtons per meter? What we're really being asked here is think about if you have a spring and you have a mass at the end of it and you pull on that mass and let go, it's going to oscillate or vibrate back and forth. For example, imagine this is a spring connected to a mass. If you pull on it so that the mass is out here now, the spring is going to get stretched. And then when you let go, it's going to go back and forth, back and forth, back and forth until it diminishes. That's called damped motion. But what we're really looking at is imagine in a perfect world without friction, what would happen? When you let go right here, it would oscillate back and forth, back and forth, back and forth, over and over again. And the period of oscillations is the time it takes when let go to oscillate once and then back to its original spot. So that's what we're trying to find out, the time, or we're looking at the time here. So for this problem it says, the period of oscillations of a mass moving in simple harmonic motion is, so the period is proportional to the square root of the mass m, proportional to the square root of the mass m, and inversely related to the square root of the spring stiffness K. Well, you know what? If we're using spring stiffness K, we should probably, instead of using K for our constant of variation, let's use another letter like C, just for this problem, so we don't confuse K and C. Again, it's completely trivial. It's up to you to decide whatever letter you'd like. Now, at this point in time, we could say to ourselves, let's apply our first condition. We're definitely going to need to solve for our constant of variation C. So how do we solve for the constant of variation C? Well, m over k is the same thing really as root m over k as far as solving. You're going to multiply by the reciprocal. So we're going to have p times the square root of k over the square root of m, and that's going to give us the C value in this problem. Again, remember, that always whenever you have a fraction, to get rid of it, multiply by the reciprocal on both sides like this, and it cancels out. Okay, so you just put the k over m over here now, and you cancel them out. Anyhow, let's go ahead and solve for C. Let's apply our conditions. We could say C equals, again, the period. In this problem, the period is given as 9.2 seconds. times the square root of k, which should really be the square root of 70, over the square root of m, which is the square root of 150. Remember, you could also lump these together as root 70 over 50. Okay, just like you could have lumped it together earlier. This is going to give us a constant of variation of a value of 6.28. Now, the next part says, what would the mass, or what mass would produce oscillations of 15 seconds when attached to a spring with a stiffness of 40 newtons per meter? So we're looking at a stiffness of 40 newtons per meter. We want oscillations of 15 seconds, and we're trying to find the mass. So let's rewrite our original formula with our C value now. So we have P equals the C value times the square root of m over k from up here. Square root of m over k. Now, we want to know what mass would give us these oscillations. What mass? So we're solving for m. So let's multiply by root k and divide by 6.28. But you'll notice that that gives us root m. But our goal in this problem is not to solve for root m, but to solve for m. So to get rid of that, all we really need to do now is square both sides of the equation here. In doing so, this becomes m equals p squared times k all over 6.28 squared. Notice I squared these two quantities to get rid of this square root, but when I square this quantity, it just gets rid of the square root completely. So I don't need the square symbol here. At this point, we're going to plug in. We're told that the oscillation period should be around 15 seconds with a spring stiffness of 40 newtons per meter. So we have an oscillation of 15 seconds and a spring stiffness of 40 newtons per meter. This would result in a mass of approximately 228 kilograms. One thing to point out, some of you may have noticed, the constant of variation in this problem is 6.28, which is actually a multiple of pi. It is 2 pi. And you'll learn more about that in physics, where the 2 pi comes from.